Hello, welcome to a new course on the basics of organic coatings for industry people. Who should attend this course? This course is for the freshers who wish to enter or who have got a job in the coating industry. This is for the business development executives in the coating companies who wish to become better or better understand their products from chemistry point of view so that it will help them to sell their products. This is also for those people who want to gain basic coating knowledge or who already have some and wish to refresh it to a small extent. So why use organic coatings? Organic coatings are usually used for really long structures. So all the networks of the pipelines which go over hundreds and thousands of kilometers can be coated using organic coatings. The versatility of organic coatings so that they are applicable to a wide variety of atmospheres is also useful. The organic coatings can also be applied to a variety of designs. So why do we have so many coatings? We can just use the same coating everywhere, isn't it? Actually, when you have different industries, you have different atmospheres, and the severity of the atmosphere will change which coating you use and how the coating should be. For example, automotives will usually have a multiple substrate composition such as aluminium, steel body, composites, fibers, etc. The marine will mostly have the aluminium hulls or stainless steel structures. These are usually much larger in size than the automotives. The offshore pipelines will be exposed, will be of different shapes and materials. They also may have a concrete structure around it. So the coatings that are used for automotives will be completely different than those for offshore pipelines because they have to be compatible with the respective substrates. It also depends on the thickness. So the offshore pipelines and marine structures are exposed to really severe marine environment, which consists of salts and oxygen, water, variety of microbes. On the other hand, the automotive, that is the cars, are usually exposed to the general atmosphere, probably rain sometimes, sunlight, and as a result they are exposed to a much less corrosive environment. Hence the coatings required for marine and offshore pipelines have to be uh, heavy duty. So they have to be thicker, they have to be of a different composition so that they can protect them from all these elements. In automotives, you cannot use a thick coating because it will increase the weight of the automotive, and because of the weight of the automotive, it will lead to lessening of the efficiency. Hence, we have to be careful that the automotives that the coatings used here are thin, but and thin and able to protect it from the atmosphere present around it. Next is also the application process. So the application in automotives is usually automated, and they have to do it on an assembly line. In marine and offshore pipelines, they have to take care to do it evenly over the large surface. It is getting automated nowadays, but the size of the structure is usually a limitation. Hence, that also decides which coating is to be used. Now let's take these three examples. We have above ground storage tanks, buildings and refineries. So all of these structures are really tall. They are exposed to a wide variety of atmosphere just in the same structure. For example, at the bottom they have a soil corrosion, here they have more of an atmospheric corrosion, rainfall, here you may have more of a sunlight corrosion, sunlight, so UV radiation. In buildings you have multiple composition, so there may be some soil corrosion, may not be. You have to protect the concrete from the sunlight. You may have steel bars which you have to protect, but they also have to be aesthetically pleasing, so you cannot use a bad color or any random color on the buildings. Refineries means they will have all kinds of fumes coming out. They will also have a temperature variation across the structures. They will have um, um, the material should sustain that the temperature from inside as well as from the outside. They have to also protect against the rainfall that may happen, the dust particles that are flowing through the wind. As a result, the refineries have a host of different uh, atmospheres, and they have to protect it. The coatings have to be compatible with all of them. So in single structure as well, we have to take care to use coatings most compatible to them. This is the reason why you have so many different kinds of coatings, because there are so many different environments that they have to protect against. In this talk, I'm going to talk about the organic coatings. ISO 12944-5 is a recently updated standard. It is highly useful and it describes everything from types of organic coatings, how they are, and how a particular coating project should be carried out. So, taking the reference of this standard, the types of organic coatings are further subdivided into two categories: reversible and irreversible. In reversible coating, the meaning is that if you coat it, you can dissolve it. Irreversible means once you coat it, you have to blast it off. You cannot bring it back to its original molecular structure. So in reversible coatings, you have a binder which is a complete polymer, that is the binder which makes your coating. The film is formed without any chemical reaction. So it is similar to the paints that we used to use in our childhood. We just mix it with water and we paint it. We are not looking at any chemical reaction happening there. Then on a molecular level, the molecules of the binder agent get attached to one another, which means that if you have these different molecules, when you coat it, they get attached to each other, and this attachment is enabled by the volatile part. The volatile part evaporates and you have a film formed on the substrate. The film can be dissolved at any point. So if you remember, in childhood we used to do paints, and if we put water on our paints, the paint would go off. The reversible coatings are similar. They will coat it, and if they want to dissolve it, they can use some kind of turpentine, ethyl alcohol, and they will dissolve this paint. So it is completely reversible. The main examples of this are chlorinated rubber, acrylic paint, and polyvinyl chloride. The second is irreversible. In irreversible, the major difference is there is a reaction. So the reaction takes place between two components, or the main component and air or temperature or atmosphere, oxygen. So when the coating is drying out, it is basically getting cured. So it gets cured physically, that is, it first dries, it can dry out by evaporation of the solvents which basically make it more homogeneous. So it will start solidifying, and you also have a chemical reaction occurring between the particles. So the chemical reaction will give rise to an entirely different particle. So I'm going to describe this further in the next few slides. As a result, this reaction is irreversible. You cannot get the original molecules back, and hence it cannot be dissolved. It has to be blasted off from the substrate. The major components of organic coatings are resin, which makes up the main coating molecular part, solvents or hardeners. So solvent will be to dissolve the coating and paint it, or the hardener, which will react with the resin. To add, in addition to this, depending on the application, you will have pigments or fillers. So to increase the mechanical strength, you may have calcium carbonate. To increase the density, you may have the talc. To increase the titania, to have UV radiation resistance, you may have titania. You may have these to change the color of the coatings, especially in cars and automotives. And mica iron oxide kaolin clay may be used to increase the coating resistance or to prevent easy water penetration. In addition to these, you may have some additives to change their properties. So the silicones help to get a better uh, resistance to moisture absorption and also better adhesion to the substrate. Rheology modifiers is used depending on whether the coating has to be sprayed or painted. Flame retardants are used in offshore platforms to prevent the fire on the platforms. Fatty acids are used to increase the molecular chain length so that the density and the compactness of the coating increases. The major types of polymers that are usually used to make coatings are acrylic, polyurethane, polypropylene, polyester, epoxy, polyethylene. There are a few more in the next slide as well. So how do we know the difference in these? Because all of them on a face value look the same. Let us start by comparing. So in acrylic, you have C attached with a double bond to an oxygen and to a single bond to oxygen. Polyester also looks the same with a double bond and a single bond. Now the difference is here you have the oxygen in the main, all of this is in the main chain. So if you are going to repeat it, you will have R attached to oxygen attached R to the carbon, then to oxygen, then to oxygen with a single bond. This will again get attached to R. So this is in the main chain. On the other hand, in acrylic, the oxygen and carbon double bonds of oxygen and single bonds are on the side chain, which means that this is going to be the major chain, CH2, CH2, CH, CH2, and all of these will be present on the branches. So when you have the oxygen, position of the oxygen changed from the uh, main chain to the branch, so this is in the main chain, this is in the branch, it will change the bond length of the molecule, because the bond strength between carbon and oxygen and the bond strength between carbon are totally different. So this will affect how the density and the molecular chain, polymer chain properties are present. As a result, this will change the way in which the polymer chains are formed as well. So next is polyurethane. In polyurethane, you have C again attached to oxygen attached to a double bond. So this is common. This is called a carboxyl group. Now the difference in polyurethane to the other two is that the C is not connected to the R, that is another ethyl unit. It is connected to nitrogen, and nitrogen is connected to hydrogen. So this is your polyurethane component. So the presence of nitrogen two carbon will also affect, because the bond strengths of Rn and Cn are totally different. In addition, you also have an oxygen in the chain. So usually it is seen that the polyurethane are much stronger, much better mechanical strength molecules than the earlier two. It is probably because of the presence of these bonds in the main chain, that is the backbone chain. Now let's see the epoxy. In epoxy, you do not have any double bond of oxygen. You do not have any nitrogen. You do have oxygen in the main chain and an OH bond on the other end. So the OH bond is a polar group. A polar group means that it is able to, it may have a remnant negative value, negative charge, and it is able to connect with any positive charge in the surrounding region. This means that when you have uh, some more molecular chains like this, the H or the oxygen will connect to any hydrogen that may be present on this bond. Similarly, any OH here will connect to the hydrogen on this bond. So this connection are weak hydrogen bonds, and they are also called van der Waals bonds. This leads to an interlocking between the epoxy chains, and this and changes the density of the epoxy chains. Such hydrogen bonds are also formed in the other areas as well, but the way in which they will be formed or where they will be formed depends on the presence of on the position of the oxygen and hydrogen. The next is polypropylene. In polypropylene, you do not have any oxygen, you do not have any nitrogen. It is entirely a carbon and hydrogen structure. So the properties over here are obviously going to be different, because here you do not have any hydrogen bonding. There's entirely CH2 bond polymer chains that are present, and mostly they lie on top of each other or get entangled like ropes. Polyethylene, polypropylene, PVC, polystyrene, these are variations of this structure. So in some cases, instead of H, you may have Cl, you may have, say, benzene rings, and those will change the molecular weight and the density of those polymer coatings. Next are these three types. You have fluoropolymer, polyurea, and alkyd. Now fluoropolymer is different because they do not have any hydrogen. They have fluorine instead of hydrogen. And the advantage here is this is a lubricating coating. Because fluorine is a heavier atom than hydrogen, the molecular weight of this is also higher, and the chains that are formed are also higher, are also of a greater density. So the fluoropolymer is an upcoming better coating. The cost is the only issue that they are facing at the moment. Next is alkyd. Alkyd also contains double bond oxygen like the polyester. The difference is here they also have OH structure. So they have they have both the properties of epoxy, that is OH, and they also have oxygen. So the difference in these is that in epoxy you had the oxygen connected to the same carbon, or you had the hydroxyl group connected to the same carbon as oxygen, but here it is connected to an entirely different structure. In polyurea, you have a difference than polyurethane, because in polyurethane every NH is connected to C double bond O, and in this C double bond is connected to R, and then that R is again connected to NH. Instead, here you have the C connected back directly to another NH. So you are eliminating the R in between, and the R will come between two NHs. So the change in position will affect the structure because now you have more number of NH bonds. The advantage in polyurize, it is able to cure faster than polyurethane because you are depending more on the curing agent that is present, and the curing will happen faster. Now let's understand how the different combinations will happen. So you may have read about different polymers. So you have acrylic polyurethane, acrylic epoxy, alkyd epoxy, polyester, polyurethane, etc. So how do these actually look? Now if you take the example of acrylic polyurethane, you have the acrylic molecule, then you have the polyurethane, then acrylic polyurethane. If you consider alkyd polyurethane, that is this, you have the alkyd molecule, then you have the polyurethane, then alkyd and polyurethane. Now if you see here, these are made, first of all, these are smaller molecules than smaller parts than the alkyd parts. So the molecular weight of these two are going to be different, weights are going to be different. The molecular chains are also going to be different. In addition, you have more oxygen atoms in the backbone chain here as compared to the acrylic. Then you also have a hydroxyl in alkyd, but you do not have hydroxyl over here. As a result, the hydrogen bonds that are formed between these polymer chains in their own structure are going to be higher in this case than in this case. This difference will lead to the two coatings, two PU coatings that are available in the market. Now we will take a look at the way in which their properties change and how they are seen in the later slides. Let's see how the curing process occurs. So we are talking majorly of the irreversible coatings. So the curing in irreversible coatings occurs in different ways. As I showed in previous slide, you will have different types of the same coating. So acrylic polyurethane, alkyd polyurethane. That depends on the molecular backbone chain. Now the difference may also be because of the curing process. So the what hardener you use will also change what coating you get. So with a simple example of polyurethane coating, in polyurethane coating, this is the resin and this is the hardener. So you have hydroxyl bonds in the resin, and the nitrogen and carbon that you have in the polyurethane chain is obtained from the hardener. So as I told you, polyurea, the hardening is easier because the hardener only will contain two NH bonds. That is how the curing process will get modified. Now in this case, what is going to happen is the hardener is going to go and connect with the oxygens. So the H over here will be eliminated and the carbon is going to go and connect to the oxygen. So these connections mean that there is an elimination of hydrogen. So there is some evolution of hydrogen gas or probably moisture, water from these structures, and this evaporation is what happens during curing. Now let's take example of epoxy. So here you have anhydride cured epoxy and amine cured epoxy. If you see in epoxy, the main thing that decides what epoxy is the resin, and the resin should always contain this triangular part. This is your epoxide ring. The epoxide ring is the triangular part where you have carbon connected to oxygen in a triangle fashion. So this is your epoxy. Any polymer which contains this triangle in the structure can be referred to as epoxide. So you have two different epoxy chains. So you have here benzene rings. Here you only have one R2. This may probably contain a benzene ring. We do not know. It is quite possible. So let's assume that this also is very similar to the structure shown over here. Now in anhydride you have two components. You have the anhydride structure where you have a ring of oxygen connected to the carbon and double bond. So you have this double bond structure, and this is present in the backbone only. So you probably are going to have this triangle somewhere around here. So they have shown it separately just for the purpose of a reaction. So these all will combine to open up the main structure. So this structure will be opened up to give you a two oxygen on each side, and this triangle will also open up where this oxygen is going to go and settle to form the two bonds. So this combination is what will give you your epoxy coating. Finally, in amine cured coating you have an NH bond. Here you do not have any nitrogen. Here you have nitrogen. So you have the NH bond, and these triangular rings are going to be opened up, and the NH is going to go and settle on these structures. Now the H from the NH is going to react with the oxygen to form the hydroxyl molecule. So the difference here lies in two parts. One is the presence of nitrogen and the way in which the two structures are formed. Now here you do not have any double bond of oxygen. Here you do have a double bond of oxygen. These molecular formations, although they may look confusing, they are the major reasons why you have the different types of epoxy coatings and how you can say which epoxy coating will suit a particular application more than the other. Now this example is for reversible coatings. This is a vinyl ester. So as I told you, ester contains the double bond C double bond O, and they have styrene. So styrene is this double bond, is this benzene ring connected with a double bond of carbon. So this structure is with the help of this initiator, with the help of this styrene, is connected together. So you have one molecule at the top, another molecule at the bottom, and in between this will go and settle. So you only are, it's like a brick. You have a brick at the top, you have the glue or the cement in between, and you have a brick at the bottom. So this will form your coating, and if you want to remove it, you have to have some reaction to remove the cement in between, that is some reaction to remove the this molecule in between. If you remove this, you have two different chains again. So we have the reversible reaction happening. You can have the two bricks back. Similarly, in case of chlorobutyl rubber, here you do not have any extra molecule that's happening. You have a catalyst. So in this catalyst, you're basically trying a uh, 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 reaction where you only have the blocks which we used to play with in the childhood, and on these blocks you will remove a particular structure and put another block. Then you remove some part and put another block. So this way you will have structure. If you want to dissolve this, you only need to add, so you need to put some water and then you can remove the blocks easily. Similarly, if you put HCl, they will react back to give the different molecules. So these are reversible coatings. So now we saw what was in the coatings, what was the molecular chain, how they look, how they react. But we don't see this when we see any structure. We only see colors, we can only feel the textures, but we don't know how the molecular chains actually fit into it. So what is inside a coating? Inside a coating, all the molecules will form such kind of chains. These are called polymer chain networks. So these polymer chains can be linear, that is like a straight rope. These can be branched, so that rope may have 2-3 strings coming out, or they may be dendritic. So dendritic would be something like leaves that come out of the structure. So when you have a combination of such polymer chains together, they will look something like this. If you have a reversible reaction, a reversible means all these chains will just settle next to each other and probably fuse together due to localized bonds. If you have a irreversible reaction, then there will be such cross-linking between the chains, and that will increase the compactness. This is shown in just 2D. This will keep happening in 3D. So you will have chain, if you have a structure, you will have chains on the structure, you will have chains inside the thickness of the coating, going slant, straight, up, down, in any direction. The way in which these chains get entangled with each other will decide how good the strength of the coating is, how good the adhesion or mechanical properties will be. Now if you have elastomers, it's just an example. What I mean to show is how the cross linking will affect your coating. So when you have a reversible reaction, or the coating polymers are like ropes which are kept on one another. So if you pull on any rope, they will separate out. If you have cross links, it is like a cot. So the cot with ropes, here the ropes are tied to each other at the corners. So these are the cross-linking regions. Now if you try to separate it, it's going to be difficult because the cross links will prevent the ropes from moving away from each other. So the irreversible coatings are usually thermoset, which means that they cannot be reversed. And the only way to remove these is by actually breaking off the coating. On the face of it, a coating composition is not only the resin hardener, as I said. If you look at the coating composition, it will have more than that. It will of course have the original structures that are required, but it will also have silica, mica, carbon black, siloxanes, depending on how the coating or what the application of the coating is required to be. So a cross section of the coating looks something like this. So as you can see, you cannot see the individual polymer chains. You cannot see the entanglements, but you can see a compact structure. You can see these mica, carbon black, these kind of fillers that are there in the coating in these bright regions. The darker regions are all coating polymer. The bright regions are all the fillers. So it is the shape of the fillers as well, and their positions, their size, which will affect the coating composition. These are bubbles that are formed if the curing, or if during the mixing of the coating there's a lot of air trapped. The air will try to move out of the coating as it gets cured, and this leads to formation of the bubbles. The typical forms of coating which are available are liquid. So you have resin and you have the hardener. You mix it in particular ratio only. You may have a powder form. So these are ready cured epoxy powders or ready cured polyurethane powders, and they will be directly coated on a heated substrate so that they will melt and fuse together. Next is a tape like form. So this is like a cello tape, that is but a large in size with much better adhesion, and they are used to wrap around the structure. So why is this done? If you remember, if you think back, sometimes you have leaking happening uh, from the taps. So to stop the leakage, you may wrap some cloth around it or some plastic sheet around it. That will prevent the water from seeping out. The wrapping tapes work in the same way. They will prevent the structure from leaking out. They act as the top layer to a top layer, and they have a very good resistance to water penetration. So even if you have any liquid coatings underneath or any powder coatings underneath, the wrapping tape will protect it as long as it is compact and properly attached. To summarize this course, coatings are omnipresent and diverse in nature. They can be modified as per the application and function required for a wide variety of industries such as marine, oil and gas, agriculture, etc. It is critical to understand how a polymer is made, what are the major polymer sites that cause the changes in the individual functions, how to differentiate between epoxy, polyurethane, polyester, etc., so that we know exactly what is going to cause the change and which coating we can use for the best protection in that particular application. This will help in better selection and recommendation of the coating, especially for those of the participants who are in charge of technical services of coating industries, and for researchers, if you want to work on the improvement of coating, you can remember these polymer sites if you're looking for which changes or what to change in that coating to make it better. Thank you for attending this course. Please let me know your feedback. Please rate this course and also let us know which other courses you would like to put up on this site. Thank you.